AP Chemistry Notes, pages 34 and 35. Let's start with a little review up here. Just to make sure, delta G is free energy. And for the main thing it does for us in this case, this tells us whether a reaction is in a good position to occur or not. That little circle called not are standard conditions, which is 25 degrees Celsius, 1 atmosphere, 1 molarity, if that applies. And negative delta G means it will occur, or at least is in a position to occur. Positive, it will not occur under these conditions. It doesn't mean it's impossible if you change conditions. And I have to go back to something we've not talked about since last year, and that's equilibrium. That is not what I wanted. Things are moving around that I did not intend. Okay. So in equilibrium, we can write an equilibrium expression, and you always do the concentration of the products raised to their coefficients over the reactants raised to their coefficients. And we'll do a special one in a moment. When doing this, you do not include solids or liquids. So no solids, no liquids. The brackets mean molarity unless otherwise stated. And if you have a very high K value, this more has to do with equilibrium review. That means when the reaction reaches equilibrium, you'll have a lot of product and not so much reactant. If you have a low K value, you will not have very much product and you'll have a lot of reactant. We'll get into some of those details about the value of K later in this lesson, and of course when we do a more thorough equilibrium review. But just to give you a rough idea, if you have a K value of something like 10,000, that means this reaction prefers to go forwards and you end up with a lot of product. If you have a K value of something like 1 times 10 to the negative 20, that means it really does not like to go forwards. It prefers to go backwards, or at least barely go forwards at all, but we'll cover that a little more later. So you'll see my little prompt is everything we did up until right now has been at standard conditions. And standard conditions, go back here. No, that's not what I want. Let's go here. Things are of course going weird in my program because it knows that I am trying to present right now. Standard conditions are 25 degrees Celsius, 1 atmosphere if it's a gas, 1 molarity if it's something dissolved. Well, what are the chances of everything falling into this? Unless you specifically create this scenario, you're not going to be at standard conditions. So now we have to do what happens if you're not at standard conditions, or like I like to call it, the not equation. And here it is. Delta G, not standard, is equal to delta G at standard plus RT ln Q. So R is the same thing as what we use for ideal gases, but notice it has different units. So right here, it's a different version of R. And notice the units are different as well. T is temperature in Kelvin, so it matches R. Ln natural log, and Q is the same thing as the equilibrium expression, but it isn't necessarily at equilibrium. So when you do an equilibrium expression and you put products over reactants, you're saying that these are the values at equilibrium, where the rates of the forward and reverse reactions are equal. When we do Q here, we don't necessarily know whether it's at equilibrium. All we're doing is saying what is the current concentration of product over reactant. So that's why it's a little different. And like I mentioned here, think of Q as the reaction quotient. in which you do products over reactants. And I give a little more detail in there in the notes. Let's see if there's anything I need to mention. Oh yeah, this is a very, it's not a huge deal, but it's something, it's one of those details you want to be careful of. If you're at equilibrium, you can use the term K and you can put things in brackets. But if you are not at equilibrium or you don't know where you are, it really wants to go to that old chart. If you're not at equilibrium or you don't know where you're at, it's best if you don't use brackets. You should use parentheses, because brackets are indicating equilibrium if you're writing a equilibrium expression. And if it's a gas, you should put a big P for pressure and then the gas. So for example, if I take this reaction here, which, what do you know, it's the Haber-Bosch reaction. If you want to write the Q expression, like I have here, you have Q, it's products over reactants, just like normal, but because we don't know anything about this system, it's best to use parentheses. And because everybody's a gas, you should do big P. So in this case, Q equals P, meaning the pressure of NH3. You still do the coefficients raised, or the chemicals raised to their coefficients, and so on. You would do P H2 raised to the third, and P into, you don't have to write the one, but I do in this case to make it clear. And that's how you do a reaction quotient expression. Let's take a look at an example. So what I have here is a reaction we saw in the last unit. Zinc solid reacting with an acid, forming a dissolved zinc ion and hydrogen gas. And we talked about this reaction. This is one in which often when you have a metal and an acid, they will react to form hydrogen gas. So, based on experience, this is likely to be a favorable reaction. But let's make sure. It says find delta G at 25 degrees Celsius. So temperature is normal, but I've changed some of the other conditions. My pressure is 750 torr, which, I mean, that's really close to 760. So that really is not a significant change, but we'll account for it. The concentration of zinc is not 1 molarity, it's 0.1. And the concentration of H plus is really low, it's 10 to the negative 4, as opposed to 1 molarity. So first, let's calculate delta G naught. In other words, calculate delta G under normal conditions, and we can do that using summation. And page 635, it ends up being quite easy considering that everything is a 0 except for the zinc plus 2 ion. And you end up getting negative 141.7. So that means under standard conditions, this reaction is thermodynamically favorable. We want to see what is it under the current conditions. So next we want to find Q. I write the expression here. Products over reactants raised to their coefficients. I did not put zinc because you do not put solids or liquids. Plug in the numbers as they were provided in the problem, and you get this here. Then you plug that into the new equation, what I like to call the not equation. Here is the standard value for delta G. Here is R, temperature in Kelvin, natural log of Q. And what we get is a negative 107.2, which means it's still favorable, but just not as aggressive as it was under the other conditions. And I want to analyze what's going on there. So I'd recommend pause the video, make sure that you can do these problems on your own, and then continue. Now that we're continuing, if you look at the delta G value versus, the delta G naught value versus delta G, they're both negative, so they're both spontaneous or thermodynamically favorable, but the one at standard conditions is a more negative. That means it's more aggressive. And then I say, look at how low the H plus concentration is. Well, let's just take a look at everything else first. The pressure of H2 being 750, that's almost negligible, so ignore that. Zinc plus 2 being 0.1, okay, that's 10 times lower than standard, but that's not a huge difference. But if you look at the H plus is 10 to the negative 4. That's 10,000 times weaker than standard conditions, and that's a reactant. So it makes sense that the reaction is not as aggressive because the acid, which is a reactant, right? Let me change the color here. Here, being so much more diluted, it doesn't mean it won't happen. It's just not going to happen so aggressively. And we see that in the value of the negative 107 versus the negative 147. Continuing on. There is usually a relationship between delta G and the equilibrium constant. A delta G of 0 means you're at equilibrium. So this means that likely the forward and reverse reactions are occurring, but equally. If this is the case, if you are at equilibrium, we can make a more advanced jump and we can get rid of Q and we can now call it K. And so if we're at equilibrium, delta G is 0, Q becomes K, and you get this new equation. Now, I like this version. I like the 0 equals delta G naught plus RT. Let's see if I can make it fit. ln K. Nope. Barely. The reason I like this version is it shows understanding. It shows that you knew to make delta G 0 and you knew to change Q to K. However, you can modify this equation and you can move the RT ln K to the other side, and that gives you this version. This version is given in the equations for the AP exam. And I'm not as much of a fan of this version because it's a modification of the other equation. I would rather you be given the other equation and you need to know how to modify it. But I don't make the decision on what goes on that sheet. So I need you aware of what this is and when it's useful. So this basically is the not equation at equilibrium with a little bit of math into it. Okay. For the most part, if you see a reaction has a negative delta G, you will usually have a large K, meaning that it likes to go forward. Similarly, if you have a very big positive delta G, that means it doesn't want to go forward, so you have a K that's very small. It doesn't want to go forward. And a delta G in the 0 area means the K is going to be somewhat near 1. These numbers are not exact. They're very rough figures, depending on the particular scenario, but it's something to notice. So now that brings up, what do you do if you have a reaction that you want to occur, but it's unfavorable? In other words, the reaction does not want to happen as we have it written. There's a couple things you can do. One thing you can do is you can put an external source of energy and force it to happen. We are going to look at this first one when we get to electrochemistry, which will be a long ways from now, near the end of our new material. And basically, you can think of it this way. A battery likes to run forwards, and if you want to charge the battery, you have to push it, you have to force it backwards by putting power into it. And we'll look at why that is the case when we get there. Another example is carbon dioxide turning into glucose. Doesn't want to happen on its own. You need to add energy, and plants have the ability to do that through photosynthesis. Another way is to do what are called coupled reactions, in which you take a reaction that does not necessarily want to happen, but you couple it and intertwine it with another reaction that does want to happen. And if the overall result is a negative delta G, it will still happen. Now I need to talk about these things called intermediates because we've not done the unit on rates yet. Intermediates are chemicals in the middle of the process that you don't typically see. Normally, we just focus on what are the reactants and what are the products. And the magic that happens in here, we don't usually even worry about that magic. Well, in there are things that get created and destroyed, and those are called intermediate chemicals. Unfortunately, it's hard to stop it at that point and study them. So it makes it a very challenging area of science. So if you look at this diagram, it is attempting to explain this scenario. Let's say we want to make chemical F right here. And our reaction involves turning chemical D and E into chemical F, and it's got a positive delta G. Well, this reaction's not a good reaction. But if we can find something that shares the intermediates, it can push it forward. So if we take another reaction, in this case, this is the A forming BC reaction. If they happen to have a similar intermediate, we can push these two reactions together. They're going to happen at the same time. And it's not that we really care about making B and C. It's just a means to an end to help D and E become F. And since the overall, of course, this example is way oversimplified, but since the overall delta G is -2, it is now possible. This is very important in biochemistry and different systems like that. Okay, a little review here. The new R, and the main reason I bring up the new R is because we have a new R. So be careful. If it's a thermodynamic question, you want to use this R. If it's a gas law, then you want to use the old R. And I mentioned why not use 0.0821 because those units are wrong and it doesn't apply to what we're doing. In the homework, I have a couple of notes here, so make sure you pay attention to this when you do the homework. I think something that happens right now that can be challenging is we have so many different ways of solving for delta H, you can get confused. For example, to solve for delta H, you can use Hess law, or you could use lab data, or you could do bond energies, bond enthalpies, would be a better word. Or you could do summation, or you could use the master equation. I'll just say master equation. So how many is that? 1, 2, 3, that 4, 1, 2, 3, 4. Yeah, 5 different ways to solve for delta H. And so what can be challenging right now is when you're given a problem, you're faced with, oh, well, which method do I need to use? Ultimately, it's whichever method works. So if you're not sure, just try one. If it fails, try the next one. And usually the problem will guide you. But I'm giving you a little bit of guidance right here for number 35, tell you what to do. I've also added, please add what happens above that temperature that's stated and below that temperature. I'm expanding the question to make it a little bit more advanced. And 65, they give you the K, which means it's at equilibrium, which means you can use the modified version of the not equation. And that's something to be aware of. And that does it for pages 34 and 35.